so let's talk about expectation values now. The expectation value, or the average value, is also known as the average value of the property of the system. Okay, can be obtained by imagining you have a large number of identical systems. That means they all have the same sign. Okay. Imagine you have a large number of identical systems, they all have the same sign. Measure that property for each one of those systems. Okay, how do you get the average? The average of property A. So each one of those systems, although they all have the same sign, will not give you the same A if you measure A, right? Because of the probabilistic nature of these things. So the average value of property A would just be the sum of each possible outcome. What are the possible outcomes? The eigenvalues of A. So you add up each possible outcome multiplied by the probability of that outcome. So the probability of obtaining A sub I. That's really how you take an average, right? So let me just see if we can relate that to something more familiar to you. Let's say calculating an average. Let's say possible outcomes are, okay, let's say this is representative of the outcomes. Okay, let's say you measured several times. Okay, so you got 2, 2, 3, 3, 3. Okay, and let's say if you keep doing it, you keep getting a 2 or a 3, and let's say this is a representative sample. So what's the probability that I'm going to get a 2? One, 2 out of 5 possible outcomes, 2 out of 5, right? Okay, what's the probability that I'm going to get a 3? 3 over 5, right? So what's my average? If I were to do this lots and lots of times and always get a 2 to 3 ratio, so your average A would be what? What would be the straightforward way of doing it? You say 2 plus 2 plus 3 plus 3 plus 3 divided by 5, right? But what's another way of doing this? I can say this is 2 happening twice, right? Plus 3 happening how many times? 3 times. Divided by the total number of times everything happened is 5, right? Well, I can write it this way. 2 times 2 over 5 plus 3 times 3 over 5. Okay? This is one possible outcome. This is the probability of that outcome. So this is the probability of getting a 2, right? This is possible outcome. So 3. 3 is one of the possibility, right? So possible outcome multiplied by the probability that I'm going to get a 3. So you add up each possible outcome multiplied by the probability of that outcome. That's how you get the average, right? So, question? What's not equal? Which one? The first line and the second line? This is 2 times 2, and that's 3 times 3, and the denominator is 5. Huh? Okay. Okay, I guess those 2s and 3s are confusing. Let's do 1 and 5. Okay, 1, 1, 5, 5, and 5. So what's the average here? You can say 1 times 2 over 5 plus 5 times 3 over 5. Okay. So if this is representative of a very large number of measurements, then you say 2 out of 5 will be the probability of getting a 2, getting a 1, right? So this is 1. So your possible outcome is a 1. And this would be the probability of getting a 1. Right? Provided that this particular set is representative of the whole large number of measurements. Okay? So that is your expectation value. That's how you calculate the average. Okay? So, but what do we know about the probability of A sub I? That's the summation of A sub I times C sub I squared, right? Where big psi is just C1, F1 plus C2, F2, and so on. Where F1, F2, and so on would be the eigenfunctions of whatever operator, of operator A in this case. Okay? So let's take a look at this one. We can actually prove that psi star A hat psi, or this, which you can write in bracket notation like this, is just the expectation value. Okay? Now, in most books, this is actually the expression of the postulate, and then from that you can derive postulate number 4. Okay, because this would suggest postulate number 4 that you can actually show that that's C sub I squared. Okay? But in our case, we made the assumption that C sub I squareds are the probabilities. Then we can prove this instead. It doesn't really matter. You can take one as a postulate and prove the other, or you can take the other one as a postulate and prove this. Okay, I think your textbook does use this as a postulate. Okay? So, and then the Bourne postulate is also a consequence of postulate number 4. We'll get to that in a minute. Let's look at this one right here. Okay? So let's show that that is in fact the case. Integral of psi star psi star A hat psi d tau. Okay, let's put this in bracket notation. Integral of psi star A hat. And what's my psi? C1 F1 plus C2 F2 plus and so on and so forth, right? We're going to say that A hat F1 is equal to A1 F1, where A1 is one of the eigenvalues, right? And so on. So, which one? Yeah, I have a star.
It's not supposed to be shown.
Oh, that's right. You're not supposed to show the star. Okay. Sorry. Yeah, you're right. No star because it's already inside the bracket. Correct. All right. So now, what would this be? C1 A hat F1 plus C2 A hat F2 and so on, right? And what do we do next? Operate on all of them. So C1 eigenfunction is, let's call it A1, little A1, F1, and A2 hat operate A hat F2 would give you eigenvalue A2, little A2 times F2 plus and so on and so forth. Okay? And what do we have on this side? This is going to be what? C1 F1 plus C2 F2 plus and so on. I have C1 A1 F1 plus C2 A2 F2 and so on and so forth. Okay? So what can we do? We can split this up, right, into little parts. So if you put this one and this one together, what do you get? C1 F1, C1 A1 F1 What would that be? Okay, I can pull out my A1, right? And C1 squared. Remember, this C1 has a star, and that C1 has no star. So C1 star times C1 is absolute value of C1 squared. And I can pull that out of my integral. And what do I have left? F1 star F1 beta, which is just going to be 1. It's the function. Okay. Why can you pull out the A? Because in standard notation, this is going to be integral of C1 star F1 star C1 A1 F1 beta. Okay, so this C1, A1, and C1 star, those are all constants. You can pull them out of your integral. Okay? So what about this second term right here? So that's the first term. How about this one? You can see there you're going to have a what? That's going to end up 0. Why? Because you're going to have a C1 star, C2, right? And then A2, and then you're going to have F1, F2 left inside the bracket. So that's going to be 0. So all the cross terms are going to come out 0, right? So what will happen here then? You'll just have, and this is just 1, so this is just A1 C1 squared plus A2 absolute value of C2 squared, and so on. So that's just the sum of A sub I times the probability that you're going to get A sub I. Okay, since absolute value of C sub I squared is the probability that you're going to get A sub I. And since that's the expression you get, that is the average. So that is your expectation value. So to get the average or expectation value of property A, all you have to do is this. Apply operator A on whatever psi is, multiply by the complex conjugate of psi, integrate over all space. Okay? Now, the Bourne postulate, we talked about the Bourne postulate earlier, a few lectures back. What did we say the Bourne postulate was? Psi. That psi squared, absolute value of psi squared is a probability density function, right? More specifically, we say that it's, remember we said that absolute value of psi squared dx is the probability of finding that particle between x and x plus dx, right? So let's see why that is a consequence of this postulate. That's why we did not give a number to the Bourne postulate, because we can just derive it from here. Okay, so we can say then that let's calculate the average location, average x value. How do we get that? Integral of what? Psi star x hat psi beta, right? So it should be automatic, okay? If you want to calculate the average of anything, put it between psi star and psi, integrate over all space. So what would this be? Well, it's just a multiplicative operator. So this is just psi star times x times psi beta, right? And what would that be? That's just integral of x times psi squared beta, right? And beta is really dx from negative infinity to infinity. Okay, so I'm just going to call this dx then, from negative infinity to infinity. Well, does that make sense? This is, You add, remember, definite integration is just addition over a continuous variable, right? So this is the sum of all the possible x values from negative infinity to infinity times the probability of getting each one of those possible x values. Okay, so the probability of getting a number between x and x plus dx is psi squared dx. Okay, so that explains the Bourne. That's how you get the Bourne postulate out of what we would call postulate 4. So this must be a probability. So you interpret this as probability of getting a value, a location between x and x plus x. Okay? So if you have a continuous variable, you integrate. If you have discrete variables, you sum. This one? How did I get that? That's a multiplicative operator. When you apply x hat on function f, it's just x times f.